screen sharing. So myself be the assistant professor. Mm. Let us start the class. So we have seen that nuclear models are of two types, that is liquid drop model and shell model. And we have semi-empirical math formula regarding this liquid drop model, and we have some concept of magic numbers regarding the shell model. So in the nuclear models, what we will see, why is the binding energy for nuclear almost constant? We'll try to see this thing. Why the binding energy per neutron is always constant? Why do certain nuclei emit alpha and beta particles? Do these particles do not exist inside the nucleus? So as these are not inside the nucleus, but they are emitting. Why they are emitting? We will try to see. Why are nuclei containing these numbers are more stable? Means why the nucleons containing these numbers means 2, 8, 20 of magic these numbers are more stable. We'll try to see in this lecture. So like any other quantum mechanical system, nucleus also exists in its excited states, the most stable state in the ground state, in which the nuclei are generally found. Different models will be there. These are the different models for the nucleus, which are for the nucleus, which are comparable. That is liquid drop model, shell model, collective model, optical model. Okay, these are the models that mostly we are going to discuss only about liquid drop model and shell model. In the syllabus, we have only liquid drop model and shell. Let us go into it. So nuclear models. So first model is the water drop model. The second one is the shell model. These are the two models which we are going to discuss in this lecture. We have discussed the liquid drop model. We have seen some assumptions which are uh, similar to that of the assumptions which are made in the liquid drop model, which are similar to that of the nucleus. So now we are going to discuss the shell model also. Models describe aspects of structures of nuclei and how they behave. We will see the aspects of structure of nuclei and how they behave. We will see. So water drop or liquid drop, we will say. So first model is what? Water drop or liquid drop model. Assumptions. What are the assumptions we have seen in the earlier class itself? Just summarize these things so that we will understand how the semi-empirical mass formula will exist, right? So the nuclei of all elements are considered to be behave like a liquid drop of incompressible liquid of very high density. So the nuclei of all elements, the nuclei of all elements are considered to be like a liquid drop of incompressible liquid. So with high very density liquid drop will be compared with the nuclei of elements. Okay, all the nuclei of elements which are having all the nucleus are compared with the liquid drop which is incompressible. Okay, in an equilibrium state, the nuclei of atom remains spherically symmetric under the action of strong attractive nuclear forces, just like the drop of a liquid which is spherical due to the surface tension. So the equilibrium state of the nuclei of atoms are spherically symmetric, remain spherically symmetric under the action of strong nuclear forces. So nuclear forces bind this nucleus in a spherically symmetric uh, shape, as well as the liquid drop also is spherical due to the surface tension. Okay, due to the surface tension, the liquid drop is spherical. Where the due to the spherically symmetric strong nuclear forces, these are spherically symmetric. Strong nuclear forces bind them as spherically symmetric, and surface tension will bind this liquid as spherical one. Okay, density of nucleus is independent of its size, just like the density of liquid, which is also independent of its size. So the density of liquid is independent of size, and nucleus is also density of nucleus is also independent of size. So it doesn't depend on the size. The density doesn't depend on the size of the liquid. Okay, as the size increases, maybe its density will decrease. The nucleons of the nucleus move about within a spherical enclosure called nuclear potential. So the nucleons of the nucleus which move about within a spherical enclosure called the nuclear potential barrier, just like the movement of the molecules of a liquid within a spherical rock of liquid. So the nucleons of the nucleus will move about a spherical enclosure. That is what we will call it as a nuclear potential barrier. So just like that, the movement of molecules of liquid also move within a spherical drop of a liquid. Just like the liquid will move in a spherical drop, the nucleons will move in a spherical enclosure of nuclear potential barrier. Okay. The binding energy per nucleon of a nucleus is constant. So the binding energy per nucleon so nucleus is constant, just like the latent heat of vaporization of nucleus. The latent heat of vaporization is compared with the binding energy of nucleus. Here, binding energy of here nucleus is compared to this liquid rock. Okay, the volume energy. The volume energy here, as a first approximation, we can think of volume energy. Each nucleon in a nucleus is interacting solely with its nearest neighbors. So it is tightly packed. Okay, it is tightly packed. The nucleus will be tightly packed due to the interaction of strong nuclear forces. So the volume of each nucleon in a nucleus is interacting with the nearest neighbors, whatever it may be, the proton or a neutron, they will be interacting with strong forces. Okay, energy associated with each nucleon bond is equals to u. The nucleon bond is equals to, we have taken mu, because because of because of bond energy is shared by two nucleons, therefore each has binding energy of half u. So the nucleon bond will be there, but there will be these nucleon will be shared with other two nucleons. As these are, each nucleon is shared with the other two nucleons. This binding energy of these nucleons is taken as half u, because half u is shared with the one nucleon and other half u is shared with another nucleon. Okay, that is why we have taken the binding energy of each nucleon as uh, half u. So when an assembly of spheres of the same size is packed together into the smallest volume each. So when an assembly of spheres, these are the spheres which are here. If you can see the diagram, that assembly of spheres of same size are packed together in a smallest volume. In smallest volume, we are packing these spherical sphere shapes. So each interior sphere has 12 other spheres in contact with each other. So each sphere will be contacted with 12 other spheres. Okay. It is a tightly packed assembly of identical spheres. Each interior sphere is in contact with 12 others. This is how the spheres will be contacted. The volume energy, continuation is of volume. Hence, interior nucleon in a nucleus has binding energy of 12, 12 into half u. So each sphere, as we see in here, each identical sphere is shared with or uh, contacted with 12 other spheres. So we will take each nucleon binding energy is how much? Half u, right? So 12 into half we will take. That is, interior nucleon of in a nucleus has a binding energy of 12 into 12u is equals to 6u. Okay. This is how we will find the interior nucleon in a nucleus of binding energy. Then, if all A nucleons in a nucleus where in the interior the total binding energy would be EV is equals to 6 AU. So 6 AU is a total binding energy, and EV is equals to, we will take it as A1 uh, A1A, that is A suffix 1A. Here it is a volume energy. We will take it as a volume energy. We'll say, okay. Also, we know that if nucleus is spherical, then so if the nucleus will be spherical, then how the volume will be? It will be sphere, volume of the sphere, right? Volume of the sphere is how much? That is 4 by 3 pi r cube. R is the radius, yet which is directly proportional to A mass number. That is 4 by 3 pi r cube is directly proportional to A. That is mass number of that sphere. If the nucleus will be spherical, the volume will be 4 by 3 pi r cube, which is equals to which is uh, directly proportional to the mass of the A. The next one is, first one is volume energy, and next one is surface energy. Actually, of course, some nucleons are on the surface of every nucleus and therefore have fewer than 12 neighbors. So if you observe here, if you observe here, this is the nucleon which is on the surface of the nucleus, right? It has 12 fevers of these attachments. That is the binding energy between the nucleon with the surface of the nucleus interact with fewer other nucleons than in the interior nucleus, and hence its binding energy is less. The large the nucleus, the smaller the proportion of nucleons at the surface. So the binding energy to the center of this nucleons will be less because they are at the surface of the nucleus, right? They are at the surface of the nucleus. So if you see the surface energy will be directly proportional to surface area. That is 4 pi r square. This is 4 pi r square. And if r is equals to r naught a power 1 by 3, this is radius of the nucleus. That is r naught 1 by a to the power of 1 by 3. Then the surface energy will become what? 4 pi r naught a to the power of 2 by 3. Okay? A to r naught a to the power of 2 by 3 will be the value, because r square this will be a to the power of 2 by 3. The surface energy will be minus a suffix 2 a to the power of 2 by 3. As this will be directly proportional to this, surface energy is directly proportional to a to the power of 2 by 3. If you see here, surface energy, actually, of course, some nucleons are on the surface of every nucleus, right? Every nucleus will have nucleons, and if it is in the center of if the nucleons are at the center, the binding energy for these nucleons is very high. But if you compare on the surface area, this will be less, right? And therefore, that they have the fewer than 12 layers. The surface energy uh, directly proportional to area. That is 4 pi r square. That is, if r is equals to r naught, then we will say it as r naught a power 1 by the surface energy is given as 4 by 3 r naught a to the power of 2 by 3. So here the surface energy is just analogous to the surface tension of a liquid. Okay, surface tension of a liquid, how it will be? Same will be the surface energy of this nucleus. We will consider. So next one is Coulomb energy. I think you know what is Coulomb energy. Coulomb's repulsive force are produced due to the mutual repulsions of protons. Okay, those are due to the mutual repulsions of protons, which are positively charged protons of the nucleus. Due to these repulsive forces, the binding energy is decreased. Okay, the binding energy is decreased, assuming that the nuclear charge Z is uniformly distributed. If those are uniformly distributed throughout the nuclear volume, the electrostatic potential energy will be 3 by 5. You will come to know how the 3 by 5 will come. So the Coulomb energy will be the repulsion force. Coulomb repulsion force is between the nucleons, means either neutrons or protons and protons. Neutrons are neutrally charged, so we will be having the repulsive force against protons and protons. Okay, it is important for lighter nuclei since a greater fraction of other nucleons are on the surface. The repulsion between each pair of protons in the nucleus also contributes towards decreasing its binding energy. Due to the repulsion of these protons, there will be decreasing in these binding energies. Okay, Coulomb energy, that is E suffix E, we will write. This is E suffix E. The Coulomb energy E suffix E is of this EC of a nucleus is the work that must be done to bring together Z protons from infinity into a spherical aggregate the size of the nucleus. So this EC is the Coulombic energy. This is what actually Coulombic energy is to bring the Z protons from infinity of distance into the spherical aggregates. If the nucleus is spherical, if you consider the spherical size nucleus, where the protons are at the infinity distance from the nucleus, we will try to bring out that nucleus to the to that sphere of nucleus. That is the Coulomb energy that is given as Coulomb potential. V is equals to V is equals to uh, minus E square, that is charge of minus E square by 4 pi epsilon naught R. This is charge of electron if you consider minus E, sorry. Protons of charge, that is V is equals to, if the charge is E and E, will Z we will consider, and will the repulsion force due to the repulsion force, it is taken as minus, that is E square by 4 pi epsilon naught. This is a constant and R is the radius of the nucleus. Since there are Z into Z minus 1 by 2 pairs, so we will take as pairs, we will take the Coulomb repulsion. Coulomb's energy EC is equals to Z into Z minus 1 by 1 into V by, okay, and which is equals to Z into Z minus 1 E square by 4 8 pi epsilon naught 1 by R. Okay. So this is Coulomb energy, and where here if you see, where 1 by R AV is the value of 1 by R average over all proton pairs. So 1 by RV is what? 1 by RV is the value of 1 by R average of all proton pairs. The protons are uniformly distributed throughout the nucleus of radius R. So the protons are distributed uniformly. 1 by RAV is proportional to that is 1 by R, and hence 1 by A power 1 by 3. Therefore, EC will be how much? EC will be is equals to minus A3 or A3 Z into Z minus 1 by A to the power of 1 by. Okay. Coulomb energy is negative because it arises from an effect that opposes nuclear stability. Because the Coulomb energy is negative, because how? Because it is against the nuclear stability. As it opposes the nuclear stability, Coulomb energy is what actually, it is a repulsive force between protons and protons. If the protons are repulsed, then what happens? There will be instability in the nucleus. That is why we will take the Coulomb energy as negative term. Okay, that is A3 into Z into Z minus 1 by A by A into A power 1 by 3. So the total binding energy, if you aggregate and write, the total binding energy will be like this. That is EV plus ES plus EC. That is EV is a volume energy, E surface energy, EC is a Coulomb energy, which is equals to A1A. That is, as volume is directly proportional to mass number, we have taken A1A, and surface is directly proportional to A minus A2, A to the power of 2 by 3. So surface energies, this is the volume energies. So again, Coulomb energy in the previous, we have seen that it is A3 minus A3 z into z minus 1, a to the power of 1 by 3, right? So that we have written minus a3 z into z minus 1, a to the power of 1 by 3. These are what Coulomb energies. So here the binding energy per nucleon. Per nucleon means we have to divide by mass number, that is A. So binding energy per nucleon is given by, if you divide this whole uh, energies by A, you will get A, A1, A will get cancelled, minus this A2 by 1 by 3. If you multiply A, divide A, you will get 1 by 2, minus 1, minus 1 by 3 as a numerator, but if you take into denominator, it will be A to the power of 1 by 3. Minus A3 into Z into Z minus 1, A to the power of 4 by 3, as it is divided, it is multiplied to A to the power of 1 by 3, you will get this value. Okay. So, nextly, this is about these binding energy terms actually, volume energy, surface energy, and Coulomb energy. We will try to find this A1, A2, A3 also. If you see this one, these, these are the empirical binding energy per nucleon. These are the empirical binding energy per nucleon. This ferrous will have more stability of binding energy, that is Fe 26 and 58. Comparatively, all binding energy. In the last class also we have discussed, here from 2 to 20 there will be a fluctuating increase. From 20 to 40 means mass number, I'm saying. From 20 to 40 it is gradually increasing, and 40 to 50, 56 will be the most stable state of all the nucleons, all the nucleus, that is iron, and it is gradually decreasing as the mass number is increasing. Okay, it is gradually decreasing as the mass number increases due to the heavier nucleus. Okay, so theoretical binding energy per nucleon. This is the theoretical binding energy per nucleon. So let us see the corrections to the volumes here, to the to the terms, to the formula. That is, correction one is when the neutrons, that is asymmetric energy. Okay, correction to the formula for asymmetric energy. When the neutrons in the nucleus outnumber the protons, which means that higher energy levels to be occupied than would be in a, would be the case in N and capital N and capital Z are equal. When the neutrons in the outnumber of protons, sorry, when the neutrons in the nucleus outnumber the protons, when the neutrons are more than protons, which means the higher energy levels to be occupied than would be the case in if N and Z are equal. Okay. Neutrons and protons spin is half fermions but obey Pauli exclusion principle. If other factors were equal, ground state would have equal number of protons and neutrons. So if other factors are equal, these must be, protons and neutrons must be equal. Okay. So here if you see illustration, neutrons and proton states with same spacing, epsilon. Process represents initially occupied state in the ground state. If 3 protons were turned into neutrons, the extra energy required would be 3 into 3 epsilon. That is, in general, if there are nz excess neutrons over the proton, then the extra energy is z minus 1 by z minus n by 2 square epsilon. That is relative to the z equals to n. If the number of neutrons increases, then they will try to become protons, and the energy needed for that one is this one, z minus n by 2 into whole square if there are NZ excess neutrons. Okay. Correction to the formula. The first correction is when the neutrons in the nucleus outnumber protons, which means the higher energy levels to be occupied than what would be the case if N and Z were equal. Okay. So the binding energy delta E is equals to number of new neutrons into energy increased by mu naught. So delta E is equals to, we will take it as half N minus Z, that is half N minus Z into epsilon by 2. That will be epsilon by 8 into N minus Z. Because N minus Z, comma, N minus Z square is equals to N minus 2Z square. The greater the number of nucleon in a nucleus, the smaller is the energy level space. Okay? As a the number of nucleons in the nucleus is higher, then the smaller the energy level spacing. Energy level spacing will be very small with epsilon proportional to 1 by. So it will be proportional to 1 by. Symmetric energy due to difference between N and Z. Due to the difference between N number of neutrons and number of protons, due to these difference, the delta is that EA, the asymmetric energy E2 is given as minus delta E, which is equals to minus A4 A minus 2Z whole square, 2Z square by A. This is the, okay. So next one is correction to the formula. See the pairing term. So here, correction to the formula pairing term. Next one is pairing term. As we see, the first asymmetric energy. Now we are going to see the pairing. The asymmetric energy is negative because it reduces the binding energy of the nucleus, isn't it? As they are changing, that the binding energy will decrease, right? So that's why the asymmetric energy will be negative. As for the correction to that is pairing term, the correction term arises from the tendency of proton pairs and neutron pairs to occur. So how the pairs will occur on that dependence, these will be these term will be explained. Okay. So correction, even nuclei, even nuclei are more stable and hence high higher binding energies. Therefore, nuclei as 2,4, helium 2,4, 6,12, 8,16, etc. appear as peak on the empirical curve on binding energy per nucleon. As even nuclei are more stable because here if you see 2,4, there are two protons and two neutrons. So the mass number is 4, that's why. Here, if you see the carbon, 3 neutrons and 3 protons, the mass number, sorry, 6 protons and 6 neutrons, the mass number is 12. 8 protons and 8 neutrons, mass number is 16. So these are having very stable state of nuclei where these are most stable, okay, most stables in the nucleus, stable states in the nucleus. That's why we'll you can see the higher peaks of this binding energy curves. Okay. The pairing energy EP is positive for even nuclei. So the pairing energy EP will be positive, okay, for the even nuclei. The pairing energy EP is 0 for odd, even and even odd nuclei. If one is odd and one is even nuclei, then the pairing energy will be 0. The pairing energy EP is negative for odd or nuclei. Odd or nuclei, the pairing energy is negative. You can see here which are stable, which are unstable. Here B5, B10. These are not even. This is odd number, right? 5, 10. The mass number is double of the proton number, but this is stable, but not as even stable, even nuclei. Okay. Here also, if you see the isotope of that, it is 511. It is also stable. Proton pin. It will be unstable 12, 5 to 512 as the number of neutrons are increased, and it is stable. Carbon will be stable, and this is also stable. So the pairing term can be the nuclei with even number of n or even number of protons more tightly bound. So the uh, the nuclei with even number of protons or even number of neutrons are more tightly bound. Only four stable nuclei, the proton and neutron have different energy levels, small overlap of wave functions, 2 p of n in same level with opposite values of jz, as as spin states, that is symmetric spatial, uh, that is maximum overlap, uh, maximum binding energy because of the short range attractions. This will be electron will be pairing term will be positive, and electron, even will be positive. Even odd is 0, and odd is negative. This is how the pairing term will be. The correction to the formula, overall correction to the formula, if you see the overall correction of this formula, the pairing energy EP is given by the relation EP is equals to plus or minus 0, uh, that is A5 by A to the power of 3 by 5. The semi-empirical mass formula, overall formula, if you want to write, the formula will be like this. It is A1A, that is volume term. This is A2 A to the power of 2 by 3, that is surface term. A3 Z into Z minus 1 by A to the power of 1 by 3, that is Coulomb term, sorry. A4 A to the power of minus 2Z by 2Z whole square by A, that is asymmetric term. The pair term is plus or minus comma 0. A to the A5 A suffix 5 A to the power of 3 by 4, that is pairing term. These are the 5 terms which combine to give the semi-empirical mass formula. This one is very much important, and A1 value is 14.1 mega electron volt, whereas A2 is 13.0 mega electron volts, and A3 is 0.595 mega electron volts, and A4 is 19.0 mega electron volts, and A5 is 33.5 mega electron. So this is about the semi-empirical mass formula in the terms, the volume term, the surface term, the Coulomb term, and the symmetric term and pairing term. These are the 5 terms which combine to give the semi-empirical mass formula of the binding energy. Okay. So, let's see the main achievements of this liquid drop model. So it explains the binding energy of large number of nuclei. Okay, large number of nuclei was explained. Binding energy was explained by using this liquid drop model. Explains the fusion and fission processes nicely. This explains the fusion and fission processes nicely. Explains energies of radioactive decays, fission and fusion. So this explains the radioactive decay of these fusions and fusions. Okay. Applications of liquid drop model or water drop model. Nuclear fission, a very large nuclear breakup, nuclear fission, fusion, very small nuclear fused together. These are the two applications of liquid drop model. Drawbacks of liquid drop model. It is not stable to explain the magic numbers. So it is not stable to explain the magic numbers. What are magic numbers? We'll see now. So it is not able to explain excited states also. It is not able to explain the excited states also. It is not able to calculate the nuclear spins. Okay. Let us dive into the other model, a shell model, which is very important. Let us see these models. We try to explain this model. Uh, the basic assumption of a liquid drop model is that each nucleon in a nucleus interacts only with its nearest neighbors like a molecule in the liquid. So we have discussed the liquid drop model. In that liquid drop model, we have assumed, we have seen that we have compared that liquid drop liquid drop neighboring interactions with the nucleon interactions in the nucleus, right? So in a shell model, what we will see in a shell model, each nucleon interacts chiefly with, with a general force field produced by all other nucleons. So in this model, we will see the interaction of general force field. General force field produced by all other uh, nucleons. Okay. So the atoms with 2, 10, 18, 36, 54, and 86 electrons have all their electron shell completely filled. So the atoms with these numbers, that is 2, 10, 18, 36, 54, and 86 electrons have their electron shell completely filled. These are completely filled electrons. Okay. In the same way, nuclei that 8, 2, 8, 20, because 2s to 2p6, like that. 1s to 2s to 2p6. You see 1s to 2s to 2p6, this is completely filled with 1s to 2s to 2p6. The number of there's a maximum number of electrons filled in p shell is 6, right? So it is 2p6. 6 will be number of filled. So maximumly filled. This is filled, and s will be having two number. So it is 1s and 2s are orbits are totally filled, and also 6 filled. That's how these are all completely filled atoms. But if you see in the same way, nuclei having 2, 8, 20, 28, 50, 82, and 126 neutrons. So here the neutrons and protons, the number with the nuclei of 2, 8, 20, that is helium, like that. Helium, oxygen, 20, 28, 50, 82, 126 neutrons and protons are more abundant than other nuclei of similar mass numbers, suggesting that structures of more structures are more stable. Okay. So here if you see, these are the nuclei which are stable, more stable. These structures having these terms will be more stable. So it is observed that the nuclei having either the number of protons z on the number of neutrons uh, n equal to a minus z equal to one of the numbers 8, 2, 8, 20, 50, 82, and 126 are more stable than their neighbors. These numbers are called magic numbers. So the number of protons and neutrons, which are having number like 2, 8, 20, 50, 2, 8, 20, 50, 82, and 126. So these numbers, having these numbers are more stable. Okay, these are more stable. Hence, these will be called we will call it as magic numbers. The numbers which are having 2, 8, 20, 50, 82, and 126, which are called as magic numbers, or we will call it as a shell numbers also. We will call it as shell numbers also. The number of protons and neutrons which are having these numbers will be magic numbers or shell numbers. Means if you take 2, that is helium, right? The number of protons are 2. So that's how we will this one will be a magic number for magic number, which is more stable. The helium atom will be more stable comparatively to beryllium. Okay? the neighboring nuclei. With the comparatively with the neighboring nuclei, the numbers which are having 2, 8, 20, 50, 82, and 126 are more stable. Main assumptions, if you see, so the assumptions which are made with the shell model are easy. So uh, nucleon forms subshells and shells within the nucleus. So nucleons will forms subshells and shells within the nucleus. Within the nucleus only there will be subshells and shells. Okay, the shell with the nucleus get closed with the suitable number of neutrons. The shell with the nucleus get closed with the suitable number of nucleons. Each nucleon is supposed to possess a spin angular momentum of h cross by 2. So each nucleon will have spin angular momentum of h cross by 2 and orbital angular momentum as 1 h. Okay. This theory assumes that LS coupling holds only for very lightest nuclei in which the L value necessarily small in their normal configuration. So the L value must be small in their normal configuration. As this theory holds only for the very lightest nuclei. The heavier nuclei exhibit JJ coupling. For, for the lightest nucleus, this will be LS coupling. For the heavier nucleus, it will be a JJ coupling. Okay. So first assumption is that nucleons forms the subshells and shells within the nucleus. Subshells and shells are formed in the nucleus itself. The shell within the nucleus gets close to the within a suitable number of nucleons, and each nuclei is supposed to possess. So every nuclei is possessing spin angular momentum h cross by 2 and orbital angular momentum Lh cross. And for very lightest nuclei, there will be LS coupling for the smallest L values, and for heavier nuclei, the coupling will be JJ coupling. Okay. So other assumptions are, it is assumed that nucleons move in its orbit. I hope you are getting here. We are comparing these nucleons with the shells of a of shells of a stability. Okay. Here, if you see, it is assumed that the nucleons move in its orbit within the nucleus independently of other nucleons. So how the nucleons will move? Within its orbit within the nucleus. So nucleons will be having some orbits like SPD. Those will be moving around, moving in the within the nucleus in those orbits only, okay, independently of other nucleons. The orbit is determined by potential energy function. So how the orbit is determined? The orbit is determined by the energy function V of R, that is potential energy function V of R, which represent the average effect of all interaction with other nucleons and is same for each particle, and which represent the average effect of all interactions with other nucleons and is same for each particle. Each nucleon is regarded as an independent particle, and interaction between a nucleon is considered to be small perturbation. So each nucleon is regarded as an independent particle. How it is regarded? It is regarded as an independent particle, and the interaction between a nucleon is considered to be a small perturbation. Okay? And the interaction between nucleons is considered to be a small perturbation. On the interaction between a nucleon and the potential field, there is a direct analogy between the theoretical treatment of a nucleus and electron in an atom. So we are taking the analogy between the theoretical treatment of a nucleus to the electron in an atom. Atom electrons, there will be shells, right, to move those electrons in SPD or orbitals. In the same manner, we will taking the theoretical analogy with the nucleus. Okay, so there will be a direct analogy, direct similarity, you can say, similarity between these two models, that is nucleus of and electron in an atom. So this is how these will be. If you see this one, you see quantum energy states. These are quantum energy states of potential, including angular momentum effects. Okay? These are quantum energy states. One is, this is 2s, 2p, and 1s. This is 1p in 1d. This is 2p, 1f. These are the spin orbitals, right? Spin orbitals. So if you see, 1s will be having two electrons, as you know, means one proton, it can accommodate only two electrons, that is spin up and spin down electrons. If you see, for two, it is stable, more stable. For 2, 4, that is 8. It is also more stable because completely filled these are. And for 20 also, these are also completely filled. For 28 also, it will be completely filled, and for 50 also complete. Further spinning from orbit effect, and these are the multiplicity of states. These are multiplicity of states for uh, how many number of uh, terms are means orbitals. Sorry, electrons are there in a shell. We will see here. So these closed shells indicated by the magic numbers of neutrons. So these are all closed shells which are indicated by the magic numbers of neutrons. These are the 2, 8, 20, 28, 50 are the magic numbers. Okay. So see the electric quadrupole moment. We see the electric quadrupole moment, measure of how much nuclear charge distribution depart from sphericity. How much nuclear charge distribution is depart from the sphericity is called electric quadrupole moment. Okay. The spherical nucleus has no quadrupole moment. So spherical nucleus doesn't have any quadrupole moment. So Q is equals to 0 will take. As the spherical shape nucleus is very spherical, then the quadrupole moment for that will be 0. While one shaped like a prolate or spheroid or egg-shaped Q is positive, then okay, for prolate that is spheroid or egg-shaped Q will be having positive Q, that is quadrupole moment. For spherical shape, the quadrupole moment is 0. For spheroid or egg-shaped Q, the quadrupole moment is positive. In an oblate, that is disc shape like or disc like spheroid, will have Q negative. Pumpkin shape or oblate will have the Q will be negative. That is, the quadrupole moment is negative. I hope you understood. When the the nucleus is in a spherical shape, the Q, that is electric quadrupole moment, is 0. And for egg-shaped or prolate shape, Q value is positive. And for the spheroid, disc-like spheroid, the Q value is negative. The nuclei of magic number N and Z are found to have 0 quadrupole moment and hence are spherical in nature. So the nuclei of N and Z are found to have 0 quadrupole moment. Magic numbers which are having with the magic numbers having this will be quadrupole moment for those magic elements will be that is 0. Okay, and hence they are spherical in nature. They are spherical in nature. Helium is spherical in nature. We can take an example of helium. Okay. So shell model is an attempt to account for existence of magic numbers and hence other nuclear properties in terms of nucleon behavior in a common force. And protons occupy separate sets of states as well as through the specifically nuclear charge. You see the quadrupole moment. What is the quadrupole moment of quadrupole moment is how much nuclear charge distribution departs from the how much the nuclear charge distribution will be there. We will see that. Accordingly, If the nucleus it will disturb the sphericity of that shape actually. Nucleus size shape will be disturbed by this Q value. If the Q value is positive, a Q value is positive means it will be the nucleus will be in a egg shaped. If the Q value is disc-like spheroid, negative, the Q value will be disc-like spheroid. If it is spherical, it will be 0. So uh, the nuclei which are having magic numbers will have quadrupole moment 0. Okay. So this is the formula you can see here by using this. This is the quadrupole moment. Q is equals to 2 by 5 z into b square minus a square. This is the prolate where Q is positive, prolate spheroid. So B is greater than 0. Sorry, B is greater than A. So here it is in spheroid shape. Uh, that is prolate spheroid. Yes, here it is as B is equals to A, and this is most stable state. Stable state actually sphere, that is Q is equals to 0. All magic numbers will have this shape, and this is what oblate spheroid where A is greater than B. So here Q is negative. The Q value is negative. You can observe using these shapes how the quadrupole moment is positive, negative, and how the quadrupole moment positive, negative, and 0. Okay. So experimental evidence of this nuclear magic numbers. Let us see the experimental evidence of these magic numbers. It has been experimentally observed that the nuclei for which N and Z are 2, 8, and so on, that is 2, 4 helium and 8, 16 oxygen are more stable than their neighbors. So we have seen by using the example, by experimenting these nuclei like helium and oxygen. If you see, helium will be more stable than the beryllium, as the beryllium is a neighboring compound only, but this helium is more stable comparatively with the beryllium and boron. And if you see for oxygen also same, the oxygen will be more stable as it contains this 8 number of protons. This is the magic number of protons, magic number of protons. So as this is magic number of protons, this will be having more, this is more stable comparatively, more stable nuclei comparatively with the nitrogen. Okay, are more stable with that. Stability also related to the natural abundance. It has been observed from the experimental data. So will be related with the natural abundance of that element. It has been observed from the experimental data that the nuclei having number of nucleons as magic number are in abundance as compared to the other nuclei. So if you see in the nature, the nucleons, the elements which are having these magic numbers uh, only more abundant, more available in the nature actually. So these are, because these are more stable, they will be available. Okay, it is observed from the experimental data that the nuclei having a number of nucleons as magic numbers are in abundance as compared to the other nuclei. So these are the examples which are abundant in the nature. That is oxygen 816, and number of protons is 8 here. If you see calcium, is number of protons is sorry, Z is 20 here. It is also a magic number. If you see uh, Pb lead, that will be N is equals to 126. Here the number of neutrons is 126, so it is more stable. So these are all magic numbers 8, 20, and 126 because, and hence these are abundant in nature. They are morely available comparatively with the other nuclei. Experimental evidence of these nuclear magic number continuation actually. This tin, if you see, tin will be having 50. Number of protons, how many protons are there? Is 50. Has 10 isotopes, stable isotopes. So tin will be having a 10 stable isotopes more than any other element. So tin will be having 10 isotopes, which are more, right? 10 isotopes doesn't have with any other elements. So these are the more than any other element. While calcium is equals to 20, Z equals to 20, that is number of protons equals to 20. We have six isotopes. Tin will be having 10 isotopes and calcium is having six isotopes. This indicates that elements with Z equals to 50 and Z equals to 20 are more than usually stable. This indicates what? This indicates the elements with Z equals to 50, Z equals to 50 and Z equals to 20 are more than usually stable. Okay. No more than 5 isotopes occur in nature for any n except n equals to 50. This is isotopes. So other than this thing, there are no more than 5 isotopes occur in nature. Okay. Where there are 6 and n equals to 82, where there are 7 for n equals to 50, except n equals to 50, there are 6 and n equals to 82. There are 7 neutron numbers of 82 and 50, therefore indicate particular stability. So neutron numbers which are having 82 and 50 are particularly stable. Okay. The double magic nuclei. What is double magic nuclei means? The number of protons and number of neutrons. Those will be the magic number. Right? Those are called doubly magic numbers. Where the number of protons or number of neutrons are in the magic number, then it means that is two 50. You have seen, right? 28, 20, 50, 82, 126. So if the protons are having 2, 8, 20, those are only magic numbers. If the protons and neutrons are both are having the same numbers, like two protons and two neutrons, those are doubly magic. Two six neutrons and six protons, those are doubly magic. Eight eight neutrons and eight protons, those are doubly magic. Okay. So 20 neutrons, 20 protons, those are doubly magic. So here if you see doubly magic nuclei, which is having number of neutrons, number of protons, both magic. This 2,4, helium 2,4 is a doubly magic. This is more stable comparatively other magic numbers, elements also. 816, oxygen 816 is also a doubly magic, and 2040, that is calcium. This is 82, 206. These are particularly tightly bound. Okay? These are particularly tightly. The binding energy of the next neutron and proton after magic number is small. The binding energy of the next proton and neutron will be very small after this magic numbers. Like take helium, beryllium. The binding energy for this will be uh, very small. Okay. Main achievements. So main achievements of this shell model. So as we see the magic numbers, as we see the magic numbers, what are the magic numbers and how the stability exists. So the shell model will the magic numbers, explain the magic numbers. It explains the magnetic moment of uh, some nuclei in isolate. It explains the ground state spin. Okay. This shell model will explain the ground state spin. It explains the great stability and high bending energy. It also explains the great stability and high binding energy. To explain the phenomenon of nuclear isomerism. It also explains the phenomenon of nuclear isomerism. Atoms having the same mass number but different and same atomic number are distinguished by certain difference in the internal structure of the nuclei called isomers. So the atoms which are having same mass number, but different atomic numbers. Atomic numbers are different, but same mass number are distinguished by certain are distinguished by certain difference in the internal structure of the nucleus of our isomers. So this magic number one is very important. To go through once again the shell model. Sorry. So what does the shell model explain is explain the stability of these numbers which are having number of protons and number of neutrons. Okay. So so mainly the shell model is presented with the nucleus of nucleons and the electrons in the shells. Okay. These are compared analogy between these two. Okay, the numbers which are having 36, 54, and 86 electrons will have the completely filled atoms. So these are very stable. Okay, let's see the limitations of this shell model. It fails to explain the stability of four stable, like as it explained about the helium, that is magic numbers, but it couldn't explain the stability of four stable nuclei, like 1, 2, hydrogen 1, 2, which is having one neutron and one proton. Helium 6, 3, 6, it is also having same number of protons and same number of neutrons, but it couldn't explain these things. And also 510, boron 510, that is 5 to 10, 5 number of protons and 10 number of neutrons. Here also the number of protons and number of neutrons are same, but it couldn't explain that, uh, explain as it explained about the magic numbers. Okay, nitrogen 714 also. If you see number of protons in this nitrogen, it will be 7, and the number of neutrons will be 7 only. That's why the mass number is 14, right? So it couldn't explain about these four stable nuclei. Does not predict correct values of nuclear spin for certain nuclei. For certain nuclei, it couldn't explain the nuclear spin. Okay, the quadrupole moment calculated using this model is also not in good agreement. The quadrupole moment is also uh, not not in good agreement. The magic the magnetic moment also shows some deviation from observed values. So magnetic moment also shows some deviations from these observed values. These are the limitations of shell model. These two models, liquid drop model and shell model, are most important ones. So just we will summarize once so that we can go through this thing. What is we have four models and nuclear models. First, we are having we we try to see we seen that binding energy per nucleons by using that liquid drop model and the magic numbers, and also we have seen these two models, liquid drop model and shell model. The water drop model or shell model, the water drop or liquid drop model is compared with the liquid drop, which is incompressible of liquid in the nucleus, and in an equilibrium the state in an equilibrium state the nuclei of atoms remains spherical symmetric under the action of strong interactive forces, just like a drop of liquid which is spherical due to surface tension. As the spherical shape occurs due to in the liquid due to surface tension, the strong nuclear forces will be cause for the spherically symmetric shape of the nucleus. The density of nucleus is independent of size. The density of liquid, which is also independent of size. So density of nucleus and density of uh, liquid is Liquid drop is independent of size, doesn't depend on size. Okay. The nucleons of the nucleus move in a spherical enclosure called nucleus potential barrier, uh, just like the movement of molecules according to spherical. So the nucleons will move in a spherical enclosure of nuclear potential barrier as that of a molecules of liquid on a spherical of liquid. Okay. So this is the binding energy, volume energy. You have to remember this volume energy terms. So how the volume energy is directly proportional to that? EV is directly proportional to A, okay? That is A1A. This is the EV is equals to A1A is a uh, uh, binding energy here. So E volume energy is A suffix A to capital A. That is directly proportional to capital A. You have to remember these 6 terms for the semi-empirical mass formula. This surface energy, which is directly proportional to a to the power of 2 by 2. Surface energy is directly proportional to a to the power of 2 by 2. Coulomb energy is directly proportional to that. This is the form, that is z into z minus 1 by 1 into e by. So that is a3 into z into z minus 1 by a to the power of 1 by. That is a to the power of minus 1 by. If you should I is EC, that is Coulomb energy, is directly proportional to mass number 1 minus 1 by. Okay? Minus 1 by. So overall, if you want to write, we will write surface Coulomb and volume energy in one term by this binding energy formula, that is E is equal to EV plus ES plus EC is equals to A1A minus A to the power of 2 by 2 minus A3 Z into Z minus by a to the power of 1 by 2. These are the Coulomb surface and volume energies. Binding energy per nucleon, if you do, per nucleon, binding energy per nucleon, so we have to divide by 10 so that you will get this one. So these are the stability curves of these nucleons which are having these number of electrons. So here Fe Ferrous 2656 is a most 2856 is a most stable because it is having it is more stable because this will be marginal. Okay. Correction to the formula. This is arsenic correction. This is the pairing term. We try to due to the if the nuclei is even, it will be positive pairing. Even odd is 0, and sorry 0 even odd will be negative. So overall, if you want to write the binding energy, that is, we will call it as a semi-empirical mass formula. So it is given as EB of A comma Z, mass number comma atomic number. The value will be like this. That is A1A, which is volume term, A2 A to the power of 2 by 3 minus A3 Z into Z minus 1 is A to the power of 1 by 3 divided by A to the power of 1 by 3. That is Coulomb term. This is asymmetric term. This is the pairing term. This is semi-empirical mass formula, which is very important to solve the problems also. So, okay. So, semi-empirical mass formula. This A1 is volume is directly proportional to A. Surface is directly proportional to A to the power of 2 by 3. And Coulomb, Coulomb energy is directly proportional to A to the power of minus 1 by 3. So, these are the achievements of the liquid drop-in and applications of liquid drop-in. These are the drawbacks. These magic numbers we couldn't explain. So shell model came into existence and it tried to explain the magic numbers. Okay. Not able to explain excited states also. So and also calculate the nuclear spin. Shell model. So as the shell model is compared with the mole, shells of a electrons which are moving around nucleus. So the atoms with these numbers are having shells are completely filled. As these are completely filled, this 2, 10, 18, 36, 54, 86, which are having this number of electrons will be completely filled. So the nuclei which is having this 8, 2, 8, 20, 28, 50, 82, 126. These are also, these number of protons and neutrons are more abundant. They are available in the nature. These are all more stable structures. So these are called magic numbers. So it is observed that the nuclei are having the protons Z of neutrons N minus Z, A minus Z equal to these numbers 2, 8, 20, 50, 82, 126 are more stable than the neighbors. These numbers are called magic numbers. Okay. These are the assumptions which are done. Nucleon forms subshells, shells within the nucleus. Okay. The shell within the nucleus is closed with the suitable number of nucleons. So nucleon supposed to possess spin angular momentum. So the nucleon will be having a spin angular momentum h plus by 2 and orbital angular momentum LH plus. So the lightest nucleus, LS coupling holes, and for the largest heavier nuclei, it will be the JJ coupling. Okay. So these are the energy levels which are shown. So if you see the analogy between the theoretical treatment of nucleus to the electron in an atom, we see the similarity between these two, and we try to use this shell model. Okay. The spherical nucleus has no quadrupole moment. If the spherical nucleus, sorry, if Q is equals to 0, the nuclei will be in a spherical shape. When Q is positive, it will be spheroid or egg shape, or when Q is negative, it will be display spheroid. Okay. The shell model is an attempt to account for the existence of magic numbers in certain other nuclear properties in terms of nucleon behavior in a common force field. Neutron and protons are separate states of states because proton interacts electrically as well as through the specifically nuclear charge. So these are the shapes we have seen in the quadrupole movement. By using quadrupole movement, these are the magic numbers which are stable and we are more abundant in the nature: oxygen, calcium, and lead. These are the experimental evidences which are seen that can have when tin have 10 stable isotopes, calcium will have 6 isotopes. Okay. These are the achievements of this shell model. It explains the magic numbers, magnetic moment of nuclei, ground state of spin, great stability of higher binding, and high binding energy. It explains the phenomenon of nuclear waves. Okay. These are the limitations. It couldn't explain the stability of 4 stable nuclei. Does not predict correct values of nuclear spin for certain nuclei. Quadrupole method calculated using this model is also not good occurring. Magnetic moment also shows some information on the observed errors. So these are the limitations of the shell model. So we'll come with other topic. Thank you for participating in the class. In the next classes, we'll try to learn the other units. This is Bhuvi. Thank you.